Hello, welcome to Chapter 5, Section 1. We're talking about transformations while we graph quadratic functions. So we talked about how to graph them using a table, the hard way, the old school way. In the last video we talked about translations, which slide the graph to the left and to the right. In this video we're going to talk about reflecting and stretches and compressions. Let's talk about reflection first. As with all transformations, the mirrors are going to be the x and y axis. You're either going to reflect across the y-axis or reflect across the x-axis. Let's start with this one. If the mirror is the y-axis, that means anything on the left is going to flip over and get reflected on the right side. And anything on the right is going to flip over the axis and be graphed on the left side. When we first talked about this, I kind of explained it this way. If I have, here's my x and y, here's my x-axis, here's my y-axis. If I have a graph that looks like the letter R, and I use the letter R because it's easy to see the reflection, this is going to flip over here and it's going to look like this and it'll be backwards. Okay, so that's what's happening. Now why did I show that? Because what happens with this one might be useful if I showed you Desmos again. So, one more time, this is my parent function, just y equals x squared. And I've got the stuff in there from last time. But now I'm going to graph this one right here, which is y equals negative x squared. And watch what happens. So that's the blue graph. That's the red graph. Blue, red, blue, red. They don't change. Both of them are in the same place. Why is that the case? That's because, and remember, horizontal, this is a horizontal reflection because you're going this way. You're going from the left side to the right side, from the right side to the left side. So this is horizontal, the direction of the transformation. This one is vertical. We'll talk about that as soon as I'm done with this one. Why? Well, remember, horizontal involves parentheses. So if my parent function is f of x equals x squared, then my new function is going to take what the change is, the input change, and square it. Well, the input change is the opposite of x. And that was the case for absolute value. It's going to be the case for every function. You replace x with the opposite of x for a horizontal translation. So if I see parentheses, I know that it is a horizontal translation. Excuse me, horizontal transformation. We talked about translations in the last video. But the math still sees this as something you can simplify. So if I did simplify it, this means negative x multiplied by itself, negative x. And a negative times a negative equals positive x squared, which is the same as just f of x. So because of the symmetry, remember, symmetry. Because of the symmetry of this parabola, the left side matches up with the right side. When I talk about the parent function, there will be times later where I'm going to reflect a quadratic function that's not the parent function. And then you will be able to see what happens. This only happens because of the parent function. And I'm going to, as I said that out loud, as I heard myself say that out loud, it happens whenever the vertex is on the y-axis, actually. So there's other times it's going to happen too, right? But if the vertex is not on the y-axis, then if it's here, it's going to be over here. It's going to flip. And we will see examples of those as we go further. Now let's talk about reflection across the x-axis. So again, the original function is f of x equals x squared. To make it into a vertical change, my g of x is going to be the opposite of whatever f of x is. So my g of x is going to be the opposite of x squared. So in my parent function, if I got x equals 3, I get 3 squared is 9. Down here, 3 squared is 9, but then I get negative 9. And remember, the order of operations, exponents before multiplying. So one of the problems that we do in Algebra 1 is we talk about this. Negative 3 squared, negative 3 squared. Are those the same? This is negative 3 times negative 3, which equals positive 9. This is the opposite of 3 squared, which is the opposite of 9, which equals negative 9. So please, the parentheses are very important. All those times I keep saying parentheses are important, this is where we're going to run into problems if we don't use them. Let's look at Desmos and see what happens with this. So I'm going to hide that one. I'm going to show you that one. Or I'm going to try to show you that one. There it is. So notice that the red got flipped down to the green. Here's the red. Here's the green. You need to go away, right? Now this is actually kind of cool because by having a negative sign in front of the x squared, this is going to get me to that idea of an like an object that's being thrown or being I don't know, whatever, like a golf ball being hit. It's going to go up, then it's going to come down. So part of that physics that we're going to see a negative sign in front of that equation we'll get to. All right, so that's a good talk about reflections. Now let's talk about stretches and compressions. So again, the parent function is going to be f of x equals x squared. All stretches and compressions are going to be f of the reciprocal of b times x. And remember, 1 over b is the reciprocal of b, because I need to know what b is to decide if it's a stretch or a compression. So my function is going to look like this: 1 over b times x, and I'm going to square that. Just like we talked about last time, you can simplify this, and that would get rid of the parentheses. But we're going to leave the parentheses in there now so that you can see that it is a horizontal transformation. All right? If b, and we're going to make b positive by putting absolute value bars around it. If b is bigger than 1, it's going to be a horizontal stretch, which means it's going to take it and it's going to pull it out sideways. And if b is less than 1, but also bigger than 0, it's going to be a compression. So let's look at let's see that on Desmos, right? So again, I still have my parent function here. Here's my function with the horizontal stretch or compression. Now you're like, but that's the same. That's because b equals 1. 1 divided by 1 times x just leaves x. So right now that is it. That's why we don't say or equal to 1. Okay, it's either got to be greater than 1 or less than 1. So I'm going to change that. I'm going to make it greater than 1. Watch what happens to the purple graph as I move this. I'm pulling it sideways. And if I keep pulling it, I've got it preset up to where it goes to 10. But if I go like, there's 9.9. If I go, go away. If I go further than that, then it's going to look flatter and flatter. But it never, ever gets perfectly flat. If I zoom way far out, and look at my scale now. Now I'm going from 0 to 100 to 200. It still has that U shape. Okay? And if I was to change my parameters here, I could keep doing that. All right? I'm going to go back to where it was. The only way that you're going to make this perfectly flat is if b goes to infinity. And remember, infinity is not a number. Okay, infinity is an idea that as soon as you think you've got a huge number, you can go further. Okay? If I go back to 0, if I can get it on exactly on 0, I didn't get it exactly on 0. Come on, go away. There. If it goes back to 0, Desmos like, I ain't going to graph it because you can't divide by 0. So Desmos is like, nope, I'm not going to do that. It just poof, disappeared. Now, here's the tricky part. I'm going to try to get this right here. If the number is bigger than 0 and less than 1, so this is 0.2, which is the same as 1 over 5. If the number is bigger than 0 but less than 1, then it actually squeezed in like that. So it made the graph skinnier. I'll pull that out when we talk about the vertical stretches. So the vertical stretches, again, my parent function is f of x equals x squared. My g of x, I just take my function, this is true for all functions, multiply it by a number. So what does it look like with quadratics? Looks like ax squared. And again, if a is negative, then the negative does the reflection. So I'm gonna make a positive. If it's already positive, that's good. So I'm gonna use the absolute value bars. If a is bigger than 1, not equal to 1, because multiplying by 1 doesn't change anything, it's a stretch. And if a is less than 1, but still bigger than 0, it is a compression. And let's show you what that looks like. Okay, so right now, and let me pick a different color here. We'll go blue, okay? So right now, I've got the same function, but if a is bigger than 1, it's being stretched up. It's right here and it's pulling it up like that. And if a is less than 1, now it's being pulled wider. I'll try to get it even lower than that. Okay? Whoops, went down to 0, which I tried to do earlier. So now that is a vertical compression, so it's squeezing it like that. Now you're probably noticing that that looks a lot like what I did with this one. A lot like it. That's because when you simplify, then a horizontal stretch or compression, when you simplify it and you get rid of the parentheses by multiplying, you end up with a vertical compression or stretch. So a horizontal compression, squeezing it this way, looks like a vertical stretch. And a vertical, a horizontal stretch looks like a vertical compression. I want you to notice that, but that's not going to be anything that you're going to be tested over. We're going to try to make it kind of clear with it. Excuse me. Okay, I know this video is already starting to get a little long because I'm talking a lot about it, so I'm going to try to do these problems here real quick without going over like too long. Okay, so remember my parent function is f of x equals x squared. What's happening right here? So it's being multiplied by -4. There are two parts to this. First, I have a vertical stretch by 4. That's this part right here. I also have a vertical reflection over excuse me, the x-axis. That's because of the negative. Do not say vertical stretch by -4. Those are two separate parts, the negative and the 4. Those are two separate parts. Okay, let's sketch a graph real quick. Here's my parent function. And how do I get my -4 times x squared? Well, you can You can stretch it by 4 and flip it, or you can just put the numbers in and see what you get. Let's put 0 in. 0 squared is 0, negative 4 times 0 is 0. So that's going to be the same spot right there. Let's try 1. 1 squared is 1. Negative 4 times 1 is negative 4, which is right here. 2 squared is 4. Negative 4 times 4 is negative 16, which is going to be way below here because it's being stretched down. So the only other point I'm going to have here is negative 1, negative 4, and then my graph is going to be very skinny, and it's going to be upside down. So it's going to look like that. G of x equals 1/2 x squared. This has parentheses, so this is horizontal. I'm multiplying by something inside the parentheses, so that means I have a stretch or compression. Before I write which one it is, I need to figure out what b is. Sometimes you're going to want to say b equals 1/2, but that's not the case. This right here is the reciprocal of b, and reciprocals are reciprocals of themselves. So what is the reciprocal of 1/2? My b equals 2. So this is a horizontal stretch by 2. One more time, here's my parent function. And if I do a horizontal stretch by 2, again, you can put numbers in and see what happens. My 0 is going to be in the same place. 1/2 times 0 is 0, 0 squared is 0. So my vertex is going to stay there. But if I try 1, 1/2 times 1/2 times 1/2 times 1 is 1/2, and I get 1/4. So it's actually going to be right here. Now that's not that helpful. Maybe it is. Let's try 2. 1/2 times 2 is 2. 2 squared. Excuse me, sorry. 1/2 times 2 is 1. 1 squared equals 1. So that's going to be right here. So one way to look at it is that this point got pulled over twice as far. So from here to here is 1. From here to here is 2. I can do the same thing right here. From here to here is 2 spaces. So its new image is going to be twice as far. 2 times 2 equals 4. So it's going to be right here. So this part of the graph is going to look like that. It got pulled over 2 times. Same thing on the other side. I'll get this point, and sorry, I'm cranking my head around to see it. And it's going to look like this. So go back. You can make a table if you want, if that helps to graph it. Or just remember that each of the x values are going to double. Right? So this point right here that was 1, 1 becomes 2, 1. This point right here that was 2, 4 becomes 4, 4. Negative 1, 1 becomes negative 2, 1. And negative 2, 4 becomes negative 4, 4. So you're gonna stretch the x values out by 2. And keep in mind that this is the reciprocal of that. We'll do just 2 more here. All right, g of x equals absolute value of 2x. Very similar to the last problem. It's using parentheses, so I know that this is horizontal. And since I'm multiplying by the x, I know it's going to be a stretch or compression. I have to figure out which one it is. Is it a stretch or is it a compression? My b is the reciprocal of that number. The reciprocal of 2 is 1/2. So this is a horizontal compression by 1/2. One more time, here's my parent function. A little sharp there at the bottom. I try to make it nice and smooth, but it didn't work. And this time I'm going to push it in half as far. I'm going to squeeze it toward the y-axis half as far. So this point is going to go halfway. This point is going to go halfway. Same thing on this side. And my new graph is going to look like this. Finally, g of x is negative 1/2 x squared. No parentheses. So this is vertical. But I've got a negative here. So that means I got two parts. So I'm going to ignore the negative for just a second. I got 1/2 x squared. This is a vertical compression by 1/2. The negative tells me I have a vertical reflection over the x-axis. So one more time, here's my parent function. At this point, I'm probably getting pretty good at that. So I'm going to squeeze all these things down this way, and I would go this way also, except I don't have a part of the graph down there, so you can ignore that. I'm going to squeeze it down toward the x-axis, and then I'm going to flip it. So this one right here, this point is at 1, 1. I'm going to move it down here to 1, 1/2, and then I'm going to flip it. It's going to end up right there. This point, I'm going to cut it in half, so it's going to go from 4 to 2. And then I'm going to flip it, and it's going to go right here. Using symmetry, I get the other two like that. Now, I'm going to cheat here just a little bit. All right? I also know that I have a point up here at 3, 9. So half of 9 is going to be 4.5 or 4.5. And then when I flip it, it's going to be right here. So even though I don't see it up here on the top, I know that it's going to be down here. And my graph is going to look like that. Please make sure you're using Desmos to double check how you graph these by hand. You'll have to do both. See you in the next video.